we have a little bit more to talk about in section 10.3. So we're still looking at parametric equations in calculus. And let's say that we have curves where x and y don't actually form a function, meaning they have a curve that doesn't pass the vertical line test. So that curve could loop around and cross itself. And at that crossing point, like if it does something like this, at this point where it crosses itself, you can draw in a tangent line going this way, tangent to like that side of the curve, but you could also draw a tangent line going that way. That's tangent to this side of the curve. So we could have more than one tangent line. In order to see where a graph crosses itself, on the AP test, if you're looking for something like this, they will likely give you the graph, or it would be on a calculator section. So we're going to use our graphing calculators to figure out how to graph these things and how to see where the graph crosses itself. So go ahead and get your graphing calculator out and change it to parametric mode. So mode, parametric, and then press Y equals. And so you're going to type in 2, and now the t is this x. It'll show up as a t in parametric mode. So 2t minus pi times sine of t. Oh, and we should still be in radian mode, unless we're actually told to put in degrees, but these should all be radians. Okay, so there's x, and then y is just 2 minus pi times cosine of t. Now, if we just zoom 6, which is like zoom standard, I don't see this graph crossing itself. So when you do zoom 6, take a look at your window to see what it counted as standard. So it has the t starting at 0, and it looks like it's going out to 2 pi. And I believe this might be a pi over 6 step. If I see on the graph, excuse me, that it doesn't look like it's crossing itself, the first thing I try is just let's look from negative 2 pi to 2 pi, because you can plug in negative t values. So negative 2 pi, let's put that in and then hit graph. And that gives you the full extent of the curve. So that's usually the fix for it. Sometimes a graph will complete itself in 0 to 2 pi or even 0 to pi. It just kind of depends. So what we're looking for on our graph is that point where it crosses itself. It looks like that is at the point 0, 2. And we can take a look at our table. Oh, get it back to 0. We can take a look at our table, and it's kind of tricky because we're not given we're given x and y at certain values of t. So the 0.02 may be on there, except it's not occurring at t equals 0. So you don't always want to go to your table to figure out where it's crossing itself. You kind of need to trust that this is happening here. We could also figure out what value of t if we wanted to. Plug in 0 for x and 2 for y, but that's going to be more work than it's worth right now. All right, so here's what I'm going to say. I'm going to say from the calculator, I can see that the graph crosses itself at 0, 2. I'll just write a note to myself, crosses itself. All right, so what are we supposed to do? Find the equations of both tangent lines at the point where the graph crosses itself. So we have the point. We just need the slope at that point. So first I'm going to find the slope, and then I will have to go back and put in 0 for x and 2 for y and see what the value of t actually is. All right, so dy dx. The derivative of y, this 2 would be constant, so it goes away. We get positive pi sine of t over, this would become 2 minus pi cosine t. And we're trying to evaluate the slope at the order pair 0, 2. Well, we need to figure out when x is 0 and when is y equal to, what was it, 2? Oops, there's a pi in there. All right, now one of these equations is easier to solve than the other. I can't solve that x equation right now because I can't like factor a t out. But here there's just a single t, so I can subtract 2 and get 0. And so 0 equals negative pi cosine t, or really just cosine t equals 0. So I can figure out, let's see, we went from negative 2 pi to 2 pi. So we should probably include negative and positive angles in our answer. So when is cosine equal to 0? That's at all of the 90-degree angles, right? Or in other words, pi over 2. Instead of 3 pi, well, I mean, I guess I could go to 3 pi over 2. But instead of 3 pi over 2, I'm going to look at it as negative pi over 2. And then I'm going to check both of those to see, because I need two values of t. One will be like, oh, the first time it's on this slope, and then the second time it's on this slope. So I need to check to see if these two values work for the x. So I just need to check now, back here, is 2 times pi over 2 minus pi times, what's the sine of pi over 2? That's 1. Is that equal to 0? Pi minus pi is equal to 0. Yes, so pi over 2 works. What about negative pi over 2? 2 times negative pi over 2 minus pi times the sine of negative pi over 2 is negative 1. Negative pi plus pi is equal to 0. Yes. If I would have plugged in 3 pi over 2, I wouldn't get the right answer, right? Because I would get 3 pi minus pi times negative 1. So I would get 4 pi. So it's 3 pi over 2 and negative pi over 2 aren't going to give me the same answer. So you do have to be careful with that. All right, so we found our two values of t. So we need to evaluate dy dx at t equals pi over 2. So that would equal pi times the sine of pi over 2 is 1 over 2 minus pi times cosine of pi over 2 is 0. So that's equal to just pi over 2. And when we plug in negative pi over 2, we get pi times negative 1 over 2 minus 0 again, so negative pi over 2. All right, so our equations, I can kind of combine them into one if I want to, since it's just plus or minus. The ordered pair that we're talking about is where the graph crosses itself, so it's 0, 2. So y minus 2 equals, I'm just going to write plus or minus pi over 2. And then it would be x minus 0, or you could just write x. Or you could add the 2 to the other side. All right. For example 2, find the equations of both tangent lines at the point where the graph crosses itself. So again, we need to go to our calculator and type in these new equations. T squared minus t and t to the third minus 3t minus 1. I'm going to go back to Zoom 6. I kind of always like to do that just to see if it's enough. And if it's not, then I go to negative 2 pi. I don't know. That's just something I do. You don't necessarily have to do that. Now I can see that the graph crosses itself. It looks like that's happening at 2, 1. And remember, 2, 1 might not show up on my table. Maybe it will. Oh, actually it does. 2, 1 does show up on my table. So that's kind of nice. But it might not have if the value for t was something that wasn't an integer, right? So I can see that t equals, actually there are two values, right? I can see t equals negative 1 and t equals 2. So from Cal, you can see this point, like the graph crosses itself as 2, 1. And I can also see equals negative 1 and 2. So in interest of length of the video, you should kind of verify algebraically just in case. I mean, I have a t to the third here, so just in case there's somehow some extra answer that would have worked. But we only need 2 values, so we saw them both on our table. Or I guess I guess what I'm worried about is like if there was another value of t that wasn't showing up immediately in the table here, like it's more negative or more positive, and you miss it just based on it. So you just have to be I would normally rely on algebra. Okay, so equations of tangent lines. So I have the points. I need the slope. So dy dx is 3t squared minus 3 over 2t minus 1. We could factor that a little bit, but nothing's going to cancel, and I don't have to take a second derivative, so I'll leave it there. And then we already figured out the t. So I'm going to start by plugging in 2. So 3 times 4 minus 3 over 2 times 2 is 4 minus 1 is 3. So I could either divide by 3, that'd be 4 minus 1, or I could say 12 minus 3 is 9, divided by 3 is 3. Our other slope is t equals, oh, not 1, sorry. No, yeah. T equals negative 1. I was looking at this point for a minute. Plug in a negative 1 there. So it'll be 3 times 1 minus 3 over negative 2 minus 1. 3 minus 3 is 0 over negative 3 is 0. All right, so one equation is y minus 1 equals 3 times the quantity x minus 2. The other equation has a 0 slope, so I'm just going to write y equals 1, or you could do point slope form still if you wanted, but it's going through the 0.21, so I know it's just y equals 1. All right, here's a new thing. To determine the distance traveled by a particle along its path, we start with the arc length formula, because if you think about this, if you look at the path of this particle, for example, if I want to know its distance traveled, since it's not a linear distance, I'm looking at essentially an arc length. So the arc length formula that we're going to use, or that we had before, was this, right? It was S equals the integral from A to B. You remember what this was? Arc length formula, chapter 7.4, I think. It was square root of 1 plus dy dx squared dx. Hopefully that sounds familiar. Okay, now this was our arc length formula. This was from, I'm just going to write chapter 7. I forget if it was 7.4. Oh, this called the curve C. Sorry, I said S. So if that curve S or C is parametric, then instead of dy dx, we have things in terms of dt, right? So let's work on this a little bit as a way to do an informal proof of getting our arc length formula for parametric equations. So 1 plus, so this is dy dt over dx dt, that quantity is getting squared. Still have a dx up. Now here's the thing. If I'm looking at arc length, everything's going to be in terms of t. So I don't want to have a dx out here. I want this to be a dt. So I need to do a little bit of algebra magic again. And kind of, I guess I kind of think of this as unsimplifying. So like, instead of having 1 plus, this will essentially be dy dt squared, dx dt squared. If the denominator here is dx dt squared, why don't we make 1 dx dt squared over dx dt squared? And I'm setting it up like a common denominator. So that's 1 plus, numerator here is dy dt squared. And I still just have this dx out here. All of this is under the square root right now. But I want to get rid of that denominator. Square root of a fraction is square root of the numerator over square root of the denominator, which happens to be a perfect square. So next step is to keep the numerator under the square root. So that's dx dt squared plus dy dt squared. You've still got a dx out here. And then instead of divided by dx dt squared, I'm going to multiply by oh, sorry, it's not squared because we're square rooting it. I'm going to multiply by dt dx. So this was, I took the square root of the denominator, right? I went boop, boop, square root of that. Instead of dividing by dx dt, I can multiply by dt dx. All right, and then these dx's cancel. And so we get our arc length formula. I'm going to keep using s, even though it said c. So s is equal to the integral from a to b of the square root of dx dt squared plus dy dt squared dt. So this is your arc length formula in parametric form. So if it's not a parametric equation, if it's just some sort of curve, we stick to square root of 1 plus dy dx squared. Things are parametric. It's x prime squared plus y prime squared, square root of that answer, integral. All right, so let's use that for the next problem. Oh, what other theorem? So if we have a smooth curve C given by x and y, which are parametric equations, and C does not intersect itself on the interval a to b, except maybe at the endpoints, then the arc length of C over the interval is our formula that we just wrote. But let's write it in terms of x prime and y prime, just to give it a different look. So x prime of t squared plus y prime of t squared dt. All right, we're going to use the calculator for this example. These often are calculator problems, but it's not necessarily always. Find the distance traveled by the point whose position is given by this parametric equation and this one on the t interval 0 to pi over 2. Okay, so all I have to do here, and this is all I have to show in the AP test, show what x prime of t is. All right, so we've got negative 5 sine of t plus 5 sine of 5t. Little chain rule in there. And then show what y prime of t is. Y prime will be 5 cosine t minus 5 cosine 5t. And then you could even write it this way. You could say the distance traveled is the integral from a to b, 0 to pi over 2. Since you've defined what x prime of t and y prime of t are clearly off to the side here, you're allowed to write it like this: x prime of t squared plus y prime of t squared. I don't always do that, but when it's something kind of long and annoying like that, then I do. And I'm kind of going to employ the same method for how I enter it into my calculator, because I don't want to have a square root and parentheses and all this stuff going on. So I'm going to go back to that trick of putting my equations into that, in this case, into the x equals and the y equals, and using those variables. So I'll show you how to do that. So type this into x equals negative 5 sine of t plus 5 sine of 5t and 5 cosine of t minus 5 cosine of 5t. I'm just going to quit. So we want the integral, math 9, from 0 to pi over 2 of the square root of, I want x prime of t squared plus y prime of t squared. And I have that in x1t, y1t. So I'm going to put, I don't even think I need parentheses. Parentheses are implied. So I'm going to go to vars, over to y vars, and down to parametric. We're normally in function, but we're in parametric mode. And they're right there. So I want that squared plus, go back there and find the y1 squared and dx, or dt. All right, so we get, a nice solid distance of 10. There are shortcuts. I always forget what these are. There's the y-var shortcut. Yeah, so you can also get, instead of going vars and through the menus, if you press alpha, let me do that again. If you press alpha and I think it's any of these buttons up here, any of these top buttons, and then you can scroll around. Here's some nice shortcuts. I just figured this out recently, so I tend not to use them because I'm not used to using them, but maybe that'll help. So that was alpha and any top key up there. All right, calculator on this one is fine. Find the arc length on the interval pi/4 to pi/3 for the curve given by this. So same thing, I would just show x prime of t is going to be -3 sine of 3t, and y prime of t is going to be cosine of 3t. Maybe on this one I will show what the values are squared, just because it's easy. Like, I'm not going to type this into my y equals ahead of time. But how you enter it in is up to you. So when you square this, you would get 9 sine squared of 3t plus 36 cosine squared of 3t. Just don't accidentally square the angles or anything. On the end. And then, like I said, I think this one's actually, I don't know, I kind of go back and forth. I could retype the whole thing, but now that I'm thinking about it, I have this on my screen. All I need to do are change the equations and change the upper and lower bounds of integration. So maybe I will do it this way. All right, so -3 sine of 3t. It doesn't really matter either way. I don't think you're going to have that much efficiency either way. So, okay, this is supposed to be pi/4, and that one needs to become pi/3. And we'll round that to 1.456. We don't have any units on this, but these would be, you know, linear lengths like inches, feet, meters, whatever. All right, now this problem, you could try it on your own if you want to, or if you're stuck, you can come back to this video and kind of work on it. I think the last part is the trickiest, but I am going to go through it. So you could either stop me here and check my key or follow along with me. Either way, you do need to do the problem. A diver leaps from the edge of a diving platform into a pool below. The figure above shows the initial position of the diver and her position at a later time. At t seconds after she leaps, the horizontal distance from the front edge of the platform to the diver's shoulders is given by x of t, and the vertical distance from the water surface to her shoulders is y of t, and they're measured in meters. Suppose that the diver's shoulders are 11.4 meters above the water, so this distance here is 11.4 meters. And we know dx dt is 0.8 and dy dt is 3.6 minus 9.8t. 4 times between 0 and A. A is the time that she hits the water. So that's happening at t equals A. Find the maximum vertical distance from the water surface to the diver's shoulders. So first of all, I need to identify what they're asking me about. The vertical distance is given by y of t. So I want the maximum y of t value. There are a few ways to do this. I guess I would say I can see that y is a parabola, right? Like that vertical distance there. I can come up with an equation for y since I have an initial condition, but I also think it's safe to say that y will reach a maximum when y of t is max when dy dt equals 0. I know that's true because I can see in the graph what's happening. And so I don't have to like test either side of that. I just know when I find that critical number 0, I'll be able to solve the problem. So when does that happen? The dy dt equation is just 3.6 minus 9.8t equals 0. T equals whatever 3.6 divided by 9.8 is. So we can round that. So that's at about 0.367. So find the maximum vertical distance. So we found the time at which that happens. What is the maximum vertical distance? So again, I could have found an equation for y, or I could say, well, we're starting at 11.4 meters, right? And then we're going to add to that the change in vertical distance from time 0 to time 0.36. Actually, you know what? I was about to write out all those decimals. Why don't we just write it as 3.6 over 9.8? Easier. Of y of t. 3.6 minus 9.8 t dt. That will tell me my maximum distance. So 11.4 plus the integral from 0 to 3.6 over 9.8, or type in the whole decimal. Don't just use the 3-place rounded version. 3.6 minus 9.8 t dt. So I'm getting about 12.061 meters. That's our maximum distance. Maximum vertical distance. And then part B says find A, find that time when the diver's shoulders enter the water. So we're trying to figure out when the vertical distance, when is y of t equal to 0? Now remember in part A we figured out when dy dt equals 0. We can figure this out by saying, by coming up with the equation for y of t. So dy, let's do it this way. So y of t is equal to the integral of dy dt, which is 3.6 minus 9.8 t dt. So we know that that's 3.6 t minus 9.8 t squared over 2 will be 4.9 t squared plus some c. We actually have that initial condition, right? We know that when t is 0, y is 11.4. So now we know that y of t is equal to 3.6 t. Well, why don't we put it in order? It's equal to negative 4.9 t squared plus 3.6 t plus 11.4. We were asking when does that hit the ground? So, or when do we hit the water? So when is this equal to 0? All right. So I can graph it. I can do Pythagorean theorem. There's all kinds of things. I'm going to graph it because I wouldn't be graphing it in parametric mode. I'd have to switch modes. So I just want to show you that. If I want to graph something and find a 0, I've got to get back to function mode. So I'm going to type in negative 4.9 x squared plus 3.6x plus 11.4. I could do quadratic formula too, either way. So zoom 6 just to see what happens. And then we're looking for that value. So second calc 0. It looks like 2, but wait, where am I? Coming down. There we go. It looks like 2, but chances are it's not. There we go. It's 1.936. So that happens A is equal to 1.936. So I should probably switch that. A is 1.936 seconds. All right, that's when we hit the water. What about part C? Find the total distance traveled by the diver's shoulders from the time she leaps from the platform until the time her shoulders enter the water. So since we were given parametric equations, total distance traveled will be our arc length formula for parametrics. So we're going to say that, I'm just going to call it S, is equal to the integral from 0 to a, or you can write out 1.936, blah, 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 blah. We're going to use all of a, though, unrounded. The integral from 0 to a of the square root of dx dt squared plus dy dt squared. You could probably just write dx dt squared and dy dt squared, but they're also not very long, so when they're short enough, I just write them in. Just feels more thorough. All right, and then I'm going to use the calculator to see what this distance is. So, I better write this down. So 9362556. Because I want to put in the whole value for my integral. So math 9, 0 to 1.936256 square root of 0.8 squared plus 3.6 minus 9.8 x quantity squared. It doesn't matter that I did not switch back to parametric mode, by the way. Okay, so I'm getting 12.946 meters. That seems reasonable. She started at 11.4, jumped up a bit, went out a bit, so it shouldn't be like a crazy amount larger than 11.4, but just a little bit. Okay, now part D is where it can get pretty confusing, I think. So find the angle between 0 and pi over 2, between the path of the diver and the water at the instant that the diver's shoulders hit the water. So we need some sort of equation with a theta. If it helps, you're looking at the fact that, like, you're looking at a right triangle, and you can orient it any way you want. I'm going to kind of look at it this way. We're looking at as x gets smaller and y gets closer to vertical this way. This angle is going to get closer and closer in, right? So this angle is going to fall in. They want this angle. So they want to know what this angle is. It was the angle between the water and the diver's shoulders. So like if she went in at this angle, which would be like a belly flop, I'd want to know what that angle was. So it's probably something close to 90 degrees, it looks like. So looking at a right triangle like this, I can figure out this angle. I'll just call it alpha. I can figure out this angle and then kind of compare it to 90 degrees. Or I can switch things around and just say, if I want this angle, like, isn't this distance still, isn't that still y of t? And isn't that horizontal distance still x of t? Right? So it's just me kind of flipping this triangle around. Basically, instead of finding this angle alpha, I'm finding its alternate interior angle right here. Okay, so I'm going to go based off of that. What equation can I set up that involves alpha, y of t, and x of t? I can set up tangent. So tangent of theta. Now, it's not y of t and x of t, though, because those are changing. So it's really the rate of change. Like, how is x of t changing and how is y of t changing? So it should be x prime of, it should be y prime of t over x prime of t. And so tangent of theta should be equal to y prime of t was 3.6 minus tangent of, 3.6 minus 9.8, goodness. What about this t? We're talking about what is the angle at the instant the shoulders hit the water. That's a, right? So that's 1.9362556 over 0.8 was no matter what, right? All right, so theta is equal to, I think I'm going to get a negative answer for this because I'm going to be I'm going to be finding the tangent of something that's not in quadrant 1 or quadrant 3. But when I checked this against the AP rubric, they just sort of said like, yeah, but it'll be positive because we're talking about a positive angle. So I'm going to find the answer in radians and just say second tangent of 3.6 minus 9.8 times 1.936256. Oops, I forgot. Gotta go back and put parentheses in here because I'm doing it all at once. Insert parentheses. Okay. That divided by 0.8. So yeah, so I'm getting a negative radian, but even though that came out negative, we're going to make it positive. So we can write the negative 1.519-ish. But our angle, just the value of it, the absolute value of it, I guess, will be 1.519 radians, and we'll start a degree symbol. So that's the hardest one because you want to just make it y of t over x of t. But we're looking at the rates of change, like how is that changing at an instant? Since it's at a specific instant, instantaneous, we're talking about the derivatives. All right, that's it for today. Tonight's homework is assignment number 31.